All right, page 4. A model of a city's population is given by this equation. P is population, T is time since 2010. Graph P of T, so graph this function using, and they give us some window measurements and sketch the graph below. These window measurements are easy. Just watch how I do it here over on the calculator. So I'm going to go to my y equals, and I'm just going to graph it like I normally would. 3, 2, 5, 0, 0, 0, parentheses 1.8, 1.18, very important, in parentheses, and we don't put it to the t, we just put it to the x. Okay, and I'm going to go ahead and hit zoom 6, and we'll just take a look. And you're going to see probably nothing. So let's go ahead now and set the window to what they said to set it to. And you'll see in here they say set x from 0 to 10, and y from 0 to, it looks like 6 zeros, so 0 to 1,000,000. So I'm going to go to the window button. Window button is the second button over in the graphing row. So I'm going to hit window there. And when I press a window, you can see my x min, x max. Well, they just told me what my x min and x max should be set to. So I want this set to a 0, this set to a 10. X scaling is fine, we'll go by ones. Y scaling, or Y, they say min 0, max this 1,000,000. 1, then 6 zeros is 1,000,000. And then you don't have to hit zoom, graph, or anything, you just, or zoom something, you just hit graph. And it automatically frames the window. And assuming they give you the right coordinates and window sizes, you'll get a nice curve like that. Okay, so let's go ahead and sketch this curve. Now, this is another one of these exponential functions. This is that a times b to the x, where our variable's up there. It's 1.8 inside for a base, so this is going to be growth. So a key point would be this y-intercept on your graph, because we kind of, in our asymptote, but that's going to be easy enough to find. So let's go ahead and sketch this, and we'll sketch it just like they have it. If they want it from 0 to 1,000,000, okay, let's go ahead and find out that y-intercept. The y-intercept is when x is 0, so you can just hit trace. You can type in the number 0, hit enter, and it tells you when x is 0, you're at that 325,000, that initial amount. So we'll just label that 325,000, like that. And we'll just have it go like this, because that's all it really does. Now, if they wanted us to find the asymptote and the line it gets really close to, well, it's going to be the x-axis. The population's never going to go negative, so if you wanted to continue on, it just gradually goes like that, just like all our exponential functions do. But again, you'd be fine just putting in this first window, this first quadrant, just like they did. Okay, and they want you to give x min and x max and label your respective axis. For this one, again, I'd just go ahead and list your domain and range to take care of that. The domain, and you're just going to do the window here. Because this equation here was modeled for the city's population since 2010, t equals 0 is 2010, so there's really no past here that to speak of. So this equation only works from 2010 going forward. So your domain is 2010 is like our 0, so is greater than or equal to 0. And your range is, well, it starts at 325,000. So 325,000 and up as the population grows. Determine the population in 2002. So let's see here. The model was created. This is measuring time since 2010. So that's 12 years. Okay, so we want to find the P of 12. What will the population be in 12 years? 1, 2, 3, 1.18 to the 12. Okay, certainly a calculator problem. I don't know what 1.18 to the 12th is, so we'll just do it on here. Okay, it's 3, 2, 5, 1, 2, 3, parentheses, 1.18, in parentheses, raised to the 12th power. All right, in 12 years, the population is going to be 2,368,467.6. We'll just leave that as 0.7 people because we won't have really a 0.6 of a person, so it wouldn't be wise to round that up. Let's see here. Next question, D. After collecting data in the year 2020, they realized the city's population could be modeled closer by this equation. So the base is changed from 1.18 up at the beginning to 1.09. What kind of issues will result in this change in the model? Well, I think what I would do is recalculate maybe. You can answer this any way you want to as long as it makes sense. For this one, I think I would calculate, let's see, in 2020, so still in 12 years, I would calculate what the real population would be, or what it turned out to be. Now raise that one to the 12th. So their new model is only about 914,116. So we'll assume, even though this wouldn't be quite accurate, one of the predictions or one of the issues that will result in the change in the model is certainly, see, answer in complete sentences. Result in the change in this model. The predicted population is almost a little more than half as much. This is just not even quite 1 million, and we had projected to be a little bit over 2 million. So it is about half, or how about the predicted population is about twice, 2 times what it actually is. And growth rate is slowing. What implications are there for taxpayers in the city? Well, if they were planning for 2 million people and they only need 1 million, then we would assume taxpayers should get a reduction. In taxes. And there's a whole paragraph you could go on here. So assuming they had been planning for these 2 million people, they probably have put a lot of resources into building their infrastructure. And when you build infrastructure, you're going to have to take out loans and make bonds, and you borrow money and stuff like that. And people end up paying more taxes for their city to be developed. But then if your population isn't growing that much, you certainly can cut down on expenses because you don't have to have the facilities. So hopefully the taxes go down. 2 more, and that'll be it for tonight. Let's see here. This is just to solve an equation. Let's see here. We got, oh man, we got a fraction here, and we got a fraction there, with this darn -6 hanging out there. So this is like one term. This is a term by itself, and this whole side here could be considered one term. This being a factor, and this being a factor of that side. And I notice I got a 5 as a denominator and a 3. So what I'm going to do is take each term times a 15. So my first term is this 1/5 times 3x plus 1. My second term is this 6 sitting here by itself. And then the third term is on the right-hand side, this 1/3 times 15 times x minus 2. So on this first one, the 5's would cancel, giving me just a 3 times 3x plus 1. Here, the -6 times 15, that's -90. Nothing cancels there. There's no denominator. 3 goes into 15 5 times, so it becomes 5 times x minus 1. Pretty easy to solve after that hard work. Distribute. Distribute. Let's get our x's all on the left. That's where I like to get them. See here, this right here is just -87. And so I want to move that negative 87 over to the right-hand side, so you just plus 87 to the left and plus 87 to the right. For x equals 82, wow, x is 82 over 4, or 42 over 81, 41. 41 over 2, like that. We'd be done. Let's see here. Solve and graph this thing on a number line. Notice this doesn't have a y in it. Okay, this is just because we're talking number line, just like so. So let's just solve it. Absolute value of x plus 1 has to be less than 4. Okay. A couple ways we can do this. I think the easiest one, though, is, so this is saying your distance from 0 is less than 4 units, or the distance x plus 1 is from 0. But the way we do it is, if I got to be less than 4 units away, it means x plus 1 is less than 4. And it also means at the same time x plus 1 could be greater than or equal to negative 4. And so, in other words, if I want to be less than 4 units away from something, I have to be bigger than negative 4, because that gets me closer to 0. And I have to be less than positive 4. And that's what it says. Your distance should be less than 4 units. So greater than negative 4, that's this one. And less than positive 4. That's that part. So there's our two equations. Now we just solve those things to figure out what the x must be. I subtract 1, x is less than 3. I subtract 1, x is greater than negative 5. And therefore, here's negative 5. Here's 3. X is greater than negative 5 and less than 3. So whatever x is, it must be some number in this range. And you can try a number out. For example, 0's in here. Try it out. 0 plus 1 is 1. 1 is less than 4. True. Try negative 4 in here, right on the edge almost. Negative 4 plus 1 is negative 3. Absolute value is 3, and 3 is less than 4. Negative 5. Negative 5 plus 1 is negative 4. Absolute value is 4. 4 is equal to 4. So yeah, that works. So there's all our answers. It didn't say to write a solution set. Okay, but when we solve something, we should. And so our solution set for this should look like this. It is a set of all x's where x is trapped between negative 5 and 3, like that. Okay, so that'd be a nice formal set notation. Or if you don't want to be formal, just give me that. Okay, and that'd be good. All right, that ends page 4.